Hello everybody, this is Dr. Christopher White and this is part 4 of streams and flooding. So now we're on to the floods. So right, what actually is a flood? Well, you'll be shocked to know that a flood is when the river's water level overtops its banks. Yeah, that's it. That's the classic definition of a flood. So essentially it means the water will exit the river channel, come over the river's banks and cover or partially cover the floodplain. Done. That simple. So what are the characteristics of a flood? Well, the first thing is floods are perfectly natural. They are totally normal. So a flood can of course cause significant damage, particularly in highly populated areas. This is something we are very familiar with in the Houston area. Of course, the capacity and the competence of a river will increase during a flood. So if you remember, capacity and competence, that's the amount of sediment a river can carry, and the maximum size of sediment that a river can carry will increase during a flood. The occurrence of floods comes from observations of discharge over time. So what we'll do is we'll monitor a river for years, and essentially we'll set a load of levels at which we know the river is going to flood, or we think the river is going to flood, or we think the river is perfectly normal. So, excuse me. If you go to a river, there's a chance you may have seen a scale attached to things like bridges, and very often that scale will be color coordinated. So it'll have something like a green area, a red area, a yellow area. So the green area is kind of like the river level during times of normal flow. The yellow area is times during high risk of a flood, and the red area essentially means the river's flooding. So those measurements, or the position of those boundaries, is based on information about the river collected over years. So a river will have different floodplains. So depending on how much a river floods, it will tend to happen less and less often. So typically very, very large floods only happen very rarely, whereas small floods will tend to happen every year. So that means a river will have what we refer to as its annual floodplain. That's when it will flood typically every year. And then it'll have another floodplain such as its 10-year floodplain. And you would expect that particular floodplain to be covered, about once every 10 years. So these are the 4 key parameters of floods. Obviously the first one is discharge. So your discharge has to exceed what we refer to as the flood stage. Once the discharge gets above the flood stage, well, that means there's so much water in the river, it's going to come over the banks. So stages itself are the height of a stream relative to its base of channel. So as you can see, here's one of these scales. Now this one hasn't got coloured areas on it, so this one's a very simplified one. But you can see the bottom of this scale will be in direct contact with the riverbed. And so this tells you essentially the height of your river. And if you have information about this river, you will know when this river essentially is at risk of flooding and when the river will start to flood based on these height measurements. Now we've already gone and discussed how the capacity of a river will increase during a flood. So the capacity is of course the total load a stream can carry, so how much sediment the river's moving. And the competence will also increase during a flood. Competence is the largest sized particle that a stream is able to carry. So all of these factors will change. So okay, what about a discharge during a flood? Well, the discharge during a flood is pretty much what you would expect. You have your base level, and obviously you're going to be happily going along your base level. When it's in your base level, your river is going to be within its channel and all is good with the universe. Obviously you're going to have some kind of event which is going to add significant amount of water into your river valley, and that water is going to eventually enter your channel, and you're going to have an increase in discharge, aren't you? Because you're going to have more water in your river, so your river is going to slowly increase in volume. And so it's going to increase in surface area. The width and the height of the river is going to increase. And there's also going to be an increase in the river's velocity as well, because your river is trying to get that water out of the system as fast as possible. So it starts to try and move that water as fast as it can. And so we see an increase in discharge because area goes up and velocity goes up. So here's our increase in discharge, and eventually our river will make it to the point where it goes above, essentially it goes above the flood stage. That's when the water will exit the river and go onto its floodplain. So now we're in a flood. Remember, as soon as the water leaves the river and goes onto the floodplain, we're in flood. The flood will continue until the discharge reaches its peak, and then slowly the discharge will decrease and the water will come back off the floodplain and return to the river channel. So it's not really a huge shock about the process involved. I mean, I think anyone can work it out pretty well. So how do we measure and calculate flow? So for streams, obviously, as we've discussed, discharge is simply area multiplied by velocity. So it's not a difficult calculation. Now in this case, this is a simplified river, and you can see that the river has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it has 10 1 by 1 meters squares. So our river is 10 meters across and 1 meter deep. So of course the area calculation would be 10 multiplied by 1, of course gives us 10, and then in order to calculate the discharge you would multiply that by the velocity. The velocity in this case is 1.1 meters per second. In terms of this river, well, okay, what's the difference? Well, we can see this was our original river depth, but you can see the amount of water in the river has increased. So now we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We're going to have another 10 on top plus a little bit extra. So it's going to be 10 plus 10.5. So about 20.5 in terms of, so it's going to be 2 meters deep multiplied by about, we'll call it 10.25. And the velocity is going to be 1.5. Okay, so if I was to do that calculation, I would do 10.5 multiplied by 2, that gives me 21, multiplied by 1.5 equals 31.5. So my discharge would be 31.5. So as we've discussed, sometimes if you see the flood stage, sometimes you will see them color coordinated, and these are the main colors and the way they're split up. So at the bottom here we have the blue area, that's referred to as current level, that's no flood. Essentially that's when everything is pretty much okay. Next we have the green area, that's minor flood in this case, and this is going to be the flood stage right here. This depth right there, that's the point where the river starts flooding, so that's the flood stage. So green is going to be a minor flood, so you'll just flood the surrounding area, it shouldn't be too damaging. As we head up, we go into the yellow area, that's the moderate flood, and then we have the red area, that's the major flood. And of course each of these zones will change depending on the river. The position of the flood stage will shift depending on the river. And each of these zones are defined by historic data for that particular river. So, we'll work out, right, at what discharge level did major floods occur? At what discharge level did moderate floods occur? And what discharge level did minor floods occur? And then we'll use those discharge levels and the water depths to work out, right, this is what this is when we should be keeping an eye out. And these flood stages are quite helpful to us because obviously, if you see your river level rising and rising and rising and rising, and it's heading up towards your flood stage, well, obviously that's the point where you're going to start mobilizing resources to try and limit the damage of the flood. Okay, so if we look at this is called a rating curve. And this is stage in feet versus discharge. So if we look here, we have the stage in feet. So this is essentially the height versus the discharge. And you will be shocked to hear this, but as the stage height increases, so does the discharge. So essentially, as your river gets deeper because there's more and more water in it, the discharge gets higher. Yeah, bet you didn't see that one coming, did you? But you can see it quite clearly. So here's our curve. So as the stage height increases, the discharge also increases. Now, this graph is actually quite helpful to us because it allows us to say, right, if we're at stage height 5, well, okay, we come across stage height 5, come across, okay, we've hit the line here, we'll come down. Stage height 5 is about 300 cubic feet per second. So you can work out the discharge based on your stage height, or you can say, right, I know the discharge, what's my stage height? You can go the other way. So if you say, right, I've got a stage height of a discharge of 100 cubic feet per second, I can come up until I hit the line, I can come across, and I can say, right, well, my stage height is just below 4 feet. Now, we've already touched on this, so capacity is the total amount of sediment our river can transport, and obviously that's going to increase during times of flood. Now, capacity is a function of velocity, because of course velocity is directly related to energy. So the higher the velocity, the more energy, and so the higher the energy, the more material the river can move. Pretty straightforward. So essentially what happens is during a capacity, if we have a tripling in discharge, so remember discharge is a function of velocity, isn't it? It's a function of velocity and area. So as the velocity increases, so does the discharge. And so a tripling of the discharge can result in a 9 to 27 times increase in the capacity. So it doesn't take much to cause your river to start transporting considerably more sediment. So next we have competence. So competence is the maximum sized class or maximum weight of class that your river can move. Obviously, the faster the current, the heavier the particle that it can transport. So once again, competence is a function of velocity. So in this case, doubling the velocity of a river results in a 64 times increase in competence. So you don't have to do very, very much to make your river suddenly start to be able to move things like houses and cars. So if we want to graph a flood and non-flood flow, okay, remember, so this is our basic graph. This is our hydrograph. We have discharge here, time here. This is our normal stream flow in non-flood conditions. Obviously, it's staying well below our flood stage. So these are two different styles of flood. So if we have a flood when we have a steady increase in the amount of water or steady increase in the velocity of our river, we're going to see the discharge suddenly get higher and higher and higher till it crosses the flood stage. Once it's crossed the flood stage, it's going to stay there for a long time, because remember, this is a gradual, steady input. So this would be a good example of something that would happen during prolonged precipitation or snow melt. The water slowly gets added, the discharge slowly increases, we make our way above the flood stage. The flood itself is quite long because the water's coming in slowly, and so we reach the peak, and the drop down is also quite slow on the other side, and now we're back below flood conditions. In contrast, if we have intense rainfall, think a very, very large thunderstorm for instance, well obviously we have our base flow. Obviously then we're going to get a very sudden, very large input of water. That's going to obviously increase the discharge. We're going to see the discharge come shooting up. We're going to see the peak is reached very, very quickly, and we're then going to see the discharge drop down very, very fast on the other side to back below your flood stage level. So these two different morphologies will be associated with different sets of conditions. Okay, so this one will give the highest flood discharge, but the flood will be shorter. This one, on the other hand, will give a lower discharge, but the flood will be longer. So these situations where we have a very, very sudden increase in discharge causing sudden, rather in some cases unexpected floods, well, they're referred to as flash floods. And flash floods are typically localized, and they're sudden floods where we have a large volume in a very, very short duration. And most flash floods are triggered by heavy thunderstorms, although they can be triggered by other situations. Something like a dam bursting, for instance, can cause a flash flood. Now, the next type of flood we have is something called urban flooding. Now, once again, urban flooding is something we're very familiar with in the Houston area. So urban flooding is where we have areas which are paved. So obviously where we have cement, where we have asphalt, that stops the water from entering the soil. And so that means the water cannot enter the soil, and so it has to sit on top of the cement, on top of the asphalt, and it can't go anywhere. And so the water has to move across the surface of the earth. So it has to move across the asphalt, has to move across the cement. Now, obviously some of the water will be taken away by storm sewers. However, there's going to be a point where the storm sewers can only handle so much water. So if you have a very, very heavy rainstorm, the storm sewers will reach capacity, and at that point, the only place the water can go is across the surface. So it's going to move across the surface of the earth, it's going to come into people's houses, etc. So in terms of urban flooding, it's all down to the amount of cement, amount of asphalt essentially inhibiting the water from infiltrating, essentially going into the soil. So both of these situations will result in these very, very steep, very, very high discharges. Because in both cases you'll get a lot of water being deposited, and in both cases that water can't go anywhere but across the surface. And when it goes across the surface, that means it enters the river quickly, so the river's discharge increases quickly, and so obviously that means your discharge is going to go shooting up and then come down rather fast on the other side. So in terms of causes of flooding, there are several causes. Now you can see there are several links here as part of the video, so I'm not going to click on them right now, but if you want to take a minute and just have a look at them, I would advise it. I would especially advise you to take a minute and have a look at this one right here. It's quite good. So there are numerous causes of flooding. So one of the first ones is snow melt. So if you have an area that has quite large quantities of snow and there's a very sudden rise in temperature, well, that can lead to substantial quantities of snow melting in a very, very short period of time. That water is going to move across the ground, because remember, the ground is probably frozen, and so that water is going to enter the river system very, very fast and cause your discharge to increase quickly. Obviously, other causes, the one we're familiar with in the Houston area, heavy precipitation, so thunderstorms, and also regional precipitation, hurricanes. So a thunderstorm is a localized event, but a hurricane, on the other hand, will dump huge quantities of water across a very, very large area. So essentially you'll have large amounts of water moving down through your river systems, and essentially that will just also lead to a flood. We also have storm surges. Now that's kind of a slightly opposite situation. Now it occurs in a hurricane, but a storm surge is when you have wind pushing seawater onto the land. So in that situation you have seawater being pushed up rivers. But once again, because you're forcing that water up the river, you're increasing the amount of water in the river, therefore you're increasing the discharge, and so that's going to lead to a flood. The next next possible reason for causing a flood is due to a volcanic eruption. So if you have some kind of volcano and it's got a large body of ice or snow nearby, something like a glacier, it can cause what's referred to as now this is going to be a terrible pronunciation, and I apologize profusely if there's anyone of Icelandic origin listening, hulups. And this essentially is when you get a volcanic eruption heating up and melting ice and snow in a glacier, causing it to melt, and obviously that really causes a huge amount of water to be released. You can have dam failures, both natural and man-made. So obviously natural dams include things like just simply fallen trees or beaver dams. They can actually hold up quite substantial quantities of water behind them, and if they break and fail, obviously that water can be released and it will flow downstream. Or of course you can have the failure of man-made dams. And the final cause of flooding is urbanization. So urbanization is going to get rid of trees, it's going to get rid of grassland, and it's going to replace it with impermeable surfaces like cement and asphalt. So obviously when you have exposed soil, so you have grassland, what happens? The rain hits the grassland, and instead of the water moving across the surface, the water begins to percolate, infiltrate the soil. Obviously that slows things down, doesn't it? Because the water goes into the soil, it becomes part of the water table, and then it goes into the river. That's going to take quite a long time. In contrast, if the water just moves across the surface, the water hits the cement, it flows across the surface, and it enters the river very, very quickly. Now, Deforestation is also part of this urbanization problem. So let's think of a tree. If there's no tree there, essentially a raindrop falls from the sky and it hits the ground. It's not impeded. However, if there is a tree in the way, a raindrop hits the top of the tree. It bounces from one leaf to another leaf, 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 and then finally it hits the ground. So it will have moved from one leaf to another several times, maybe even dozens of times. So it's actually going to slow down the rate at which the water hits the ground. Now that's going to also help to reduce the risk of flooding, because the water is taking longer to hit the ground, and therefore it's taking longer to enter the river. So deforestation and the covering over of essentially grassland by asphalt and cement obviously is urbanization, and that can obviously lead to essentially more flooding because the water moves across the surface of the earth rather than allowing the water to enter the groundwater and enter the river slowly. So what are the effects of flooding? So the effects of flooding can be at the one level geologic. So obviously we have increased velocity in our rivers during floods, and increased velocity essentially along with increased volumes of water is going to lead to increased erosion. When the water slows down, obviously the velocity is going to decrease, the volume is going to decrease, and we're going to get flooding. And so that's obviously a geologic process. But there's also, of course, going to be economic problems. Of course, flooding will damage infrastructure. It will damage houses, it will damage vehicles, and so there will be an extremely large economic cost of any large flood. There are, of course, environmental damage. So, of course, there's contaminated water. So you can have chemicals leaking into the water supply. Of course, if you have water mains bursting, that can obviously allow chemicals directly into those water mains, and that can, infiltrate the public water supply. Now then we have agriculture. Agriculture on the whole is relatively pro-flood because it wants the fresh nutrients, it wants the fresh clay and silt to be added to the soil to revitalize it. So agriculture is not completely against flooding. Now then there's health problems. So there can be infectious disease. So if we have sewer water entering the municipal water supply, that can obviously lead to a whole range of interesting and quite horrible diseases. Then of course we have changes in the ecosystem. So what we can end up with is we can end up with very large bodies of still water. In hot conditions, we know of course in the Houston area, where you have a large body of still water, of course it becomes a breeding ground for mosquitoes. And then, of course, you've got problems like malaria and West Nile to deal with. And then, of course, there's, possibly the most obvious, there's the risk of loss of life, and there's the displacement of people from their homes. So, the causes of flooding. Well, there are several causes of flooding. The first one is quite an obvious one, snowmelt. So, if we have a situation where you've had large amounts of snowfall during the winter months, and then you come into the spring and all of a sudden you have a very rapid increase in temperature, well, that's obviously going to cause a lot of that ice and snow to melt very, very quickly. That, combined with the fact that in these situations the ground will probably be frozen, means that the water will move across the surface very, very quickly and enter the rivers, leading to a flood. Obviously there's heavy precipitation, where you have large quantities of water being deposited very, very fast. That water will enter the river very, very quickly. Once again, you'll have a flood. Regional precipitation, hurricanes, exactly the same thing, just like a thunderstorm, but just on a much larger scale. You have a huge area being covered in large amounts of water. Once again, that will lead to thunderstorms, because you'll have very significant amounts of water entering your river in a very, very short space of time. Then we have storm surges. Now that's kind of a slight reverse situation. So a storm surge is where you have the wind pushing the sea up the river. And so as the sea gets pushed up the river, what does that do? Well, it increases the amount of water in the river channel. And of course, that will also lead to an increase in discharge and therefore a flood. Volcanic eruptions. So a volcanic eruption can cause ice and snow to melt if there's any kind of glacier or anything on top of the volcano, and this can lead to the formation of now I do apologize if there are any Icelandic people listening to this, that can lead to the formation of a hjullupse, which essentially is where you have a large quantity of ice melting very, very quickly due to a volcanic eruption, which causes a flash flood. Obviously, you can have dam failures, both natural or man-made. So obviously natural dams, just something like a fallen tree blocking a river, or a beaver dam. Those can actually hold back quite substantial quantities of water in some cases, and so when those fail, that can obviously allow water to flow downstream. And obviously we have man-made dams. When they fail, once again exactly the same situation, you can have quite large quantities of water flowing downstream very, very quickly. The final cause of flooding is urbanization. So urbanization essentially is the loss of grassland and trees. So it's deforestation as well. So the loss of grassland is damaging because when rainwater hits, exposed soil, some of that water will move across the soil on the surface, but some of that water will percolate into the soil. It will infiltrate the soil. Now that's going to slow down the rate at which water enters the river, because some of that water will have to infiltrate the soil, move through the groundwater, and then enter the river. That's going to take quite a long time. In contrast, if you just have concrete there, the water hits the concrete, it can't enter the soil, and so that water has to exclusively move across the surface. And so as it moves across the surface, it moves quickly, enters the river quickly, and it can lead to a flood. The other situation is that urbanization will often cause deforestation. So let's think about a raindrop. So as a raindrop falls from the sky, if there are no trees there, the raindrop hits the ground without any kind of blockage in the way, any kind of hindrance. In contrast, if a raindrop falls from the sky and it hits a tree, it's going to go from one leaf to another leaf to another leaf to another leaf to another, etc. So it's going to go from leaf to leaf as it falls from the tree. A trip that would take seconds if there wasn't a tree there can end up taking minutes. And so that's just slowing down the rate at which the water hits the ground. And once again, that's just reducing the rate at which water can make it into the river. Now, it might not sound like, that big a difference, but I'm not talking about one tree. I'm talking about hundreds or thousands of trees helping to slow down the rate at which water makes it to the ground, and therefore the rate at which the water makes it to the river. So the loss of grassland and deforestation are parts of the urbanization process, and very, very damaging because essentially it means that water will move across the surface more quickly, enter the river more quickly, and be more likely to cause flash floods. So what are the effects of flooding? Well, there are several effects of flooding. The first one is geologic. Obviously, when a flood occurs, it's going to increase the river's velocity and volume, and so that's going to lead to increased erosion. When the river slows, the velocity is going to drop, the volume is going to drop, and we're going to have deposition. So we're going to have flood deposits forming. So from a geologic point of view, that's one of the methods by which we form rocks around rivers. Obviously, there's going to be economic damage. There's going to be significant damage to infrastructure. Roads, houses, bridges are all going to be damaged by the rains, not to mention cars, trucks, etc. Environmental damage, contaminated water. So during flooding, obviously it's not uncommon to have the municipal water supply contaminated, and sometimes that can be by chemicals. Something like gasoline leaks out of a storage tank underneath a gas station, it goes into the floodwaters, and then goes from the floodwaters into the municipal water supply, contaminating it. Agriculture. Well, agriculture is kind of pro-flooding actually, because flooding essentially adds new soil, adds new nutrients and new silt and clay to the soil, revitalizing the soil. And so agriculture is not against flooding on the whole. Obviously, there's the health problems, there's infectious diseases, and there's damage to the ecosystem. So, for instance, we can have a situation where we have sewage water entering the municipal water supply, contaminating it. That can obviously lead to a whole range of diseases. And then we have a situation where we have areas that were once, well drained, suddenly find themselves being quite poorly drained. So we have bodies of water building up. And obviously in the Houston area, where you have large bodies of water building up, especially in hot conditions, those are breeding grounds for things like mosquitoes, and that obviously leads to problems with malaria and West Nile, for instance. And then, of course, we have the most obvious one of all. Floods can lead to loss of life and displacement of people from their homes. There's obviously the human aspect as well. So this is an example of a flood. So we can see this in Norilsk in Russia. So you can see Norilsk is a mining town. So each of these are essentially smelters where they're extracting the metal they want from the ore. And essentially all the stuff they don't want gets dumped into what are referred to as tailing ponds. They're essentially waste ponds. Now what you can see here is where the dam of one of these waste ponds has failed, causing a flood that's moved downstream. So you can see this is what the river looks like normally. One of the tailings ponds has failed just up here, and the water has entered the river here and started flowing downstream here. And you can quite clearly see, the dam failure has led to a flood, and you can see the contamination of the water produced by that flood. So in terms of discharge graphs, now we've already touched on these already, but it doesn't hurt to just go over them again. In terms of what we have here, you can see we have different colors on this diagram. The white color essentially is normal river level. The yellow band is action. Now that means the river hasn't flooded, but if you're, if you're in charge of the flood defense, that's the time when you start taking action. You start, mobilizing people, start putting sandbags up, that kind of thing. Then we have minor floods here in orange. We have moderate floods here in red, and major floods here in purple. Okay. Now what you can see in this case, this flood is already in the minor stage, so it's already gone over the river. But you can see in this case we have a broad, long peak. So this is being caused by some kind of gradual addition of water. So for instance, snow melt. In contrast, we have these two peaks here. We can see the discharge comes up very, very quickly in both of these instances, reaches its peak, and then comes down relatively fast on the other side. So these have been caused by sudden events, so a thunderstorm would be a good explanation for those. So okay, so obviously I'm sure you all remember this one. This is a very, very recent flood event in the Houston area. Of course, we have Harvey. So this is the track of Harvey, okay? And you can see these are the different categories. So you can see when it was out over the Gulf of Mexico, out over the Caribbean into the Gulf of Mexico, it was Category 1, became Category 2, and just as it started hitting the coast, it went from Category 3 to Category 4. And it initially hit the coast to the south of Houston, and then as you can see started migrating slowly but surely up towards the northwest. So as the hurricane moves across the Gulf of Mexico, what does it do? It picks up warm, moist air, and that essentially makes the hurricane become more and more powerful. So what the storm would try to do is, normally as the storm makes landfall, the storm would normally hit land and then it would try and go that way. It would just try and follow its path. But there was a bit of a problem. It just so happened that at that exact time there was a big high pressure area right here. So as the hurricane moves north, it tries to move north. It tries to move northwest, but it keeps hitting this high pressure region. It keeps bouncing off the side of it. So instead of being able to move northwest, it's forced to move northeast instead, because there's this big high pressure region blocking its path. So that forced the hurricane northeastwards towards Houston. The other problem is that you'll notice that the hurricane is essentially straddling the coastline as it moves northwest. Most of the time when a hurricane moves over land, it starts to lose that warm, moist air, that warm, wet air, so it starts to lose energy. However, in the case of Harvey, we have a situation where the hurricane was half on the land and half over the ocean. So it might have been dumping the water as rain on this side, but the half of it that was over the ocean was picking up new, warm, moist air. So it was adding more moisture to the hurricane. So it was constantly replenishing itself. So this hurricane was constantly keeping up the same level of precipitation over a very, very long time period. So this was a really nasty situation. It was pretty much about as bad as it could have gotten. So what happens is we find that Harvey kind of stalls over the Houston area, and it takes a very, very long time to make it over Houston. Instead of being over in the space of hours, it takes a few days to actually make it fully over the Houston area. Now, rivers obviously that would drain quite normally began to swell because there was so much rainfall going into them. The other problem was the rainfall was so prolonged that the soil became saturated. So you couldn't infiltrate any more water into the soil. So what does the water do in that situation? It just moves across the surface because it can't go into the ground. Combine that with the fact that Houston is a very heavily urbanized area. We've gotten rid of a lot of the grassland and forest in the area. And so we've essentially caused the water to move across the surface a lot faster, also increasing our rate of flooding. Now, in order to try and stop flooding, the Houston area actually has two very, very large reservoirs. They're called Addicks and Barker. And they're designed to stop water coming down along a river called Buffalo Bayou. And in theory, they should be able to hold up that water. And so they should stop that water going into the downtown of Houston and flooding it. At least that's the plan. The problem is that these dams were built at a time when the land behind them, so to the west of Houston, was not urbanized. So when those dams filled up, it also meant they could flood backwards essentially onto the grassland and into the forested land and allow them to flood as well. The problem is that those areas to the west of those dams are now urbanized. So there's houses, there's businesses there. So this meant that what happened was they had to try and hold the water in the dams for as long as they possibly could. And eventually it got to the point where the dams became so full that they had a choice. The water was either going to go over the top of the dams and flood downtown, or the water could be allowed to flood backwards and flood the area to the west of the dams. And what happened was the Army Corps of Engineers made the decision that the smart move was to let the flood water flood the land to the rear of the dam, so to the west of the dams. At the same time, the centre of Houston was already flooded anyway because the sheer quantity of water being dumped into the area and being dumped into a very highly urbanized area meant that Buffalo Bayou and several other rivers in the area quickly broke their banks and flooded the downtown of Houston anyway. So just to give you some idea, this was the view from the doorstep of my old house, and you can see these are the floodwaters of Harvey. So I live near Addicks Reservoir, and you can see this is the area that's been flooded. I was very, very lucky. I happened to own the house that didn't flood. The houses to the left of the picture, they unfortunately flooded. My house and the houses to the right of the picture, they did not. So I got extremely lucky in that particular event. So, this is what happened. Now, the thing is the Barker and Addicks dams, which essentially cover the west of Houston, they offered some protection. Now, on the northwest of Houston, you have Cypress Creek. So Cypress Creek is, once again, it's a very large river. It kind of goes from the northwest of Houston down into the center of Houston. Well, actually, no, I tell a lie. It's northwest, and it kind of goes across to the San Jacinto River. So the problem is the Cypress Creek area is getting steadily more urbanized, but it doesn't have any kind of defenses to help hold that water back. So when the Cypress Creek River started to fill up, there was no way to hold back the water, so that river went over its banks very, very quickly and very, very early. So the west side of Houston got pretty badly hit. The center of Houston got pretty badly hit. What about the eastern side of Houston? Well, okay. So let's have a quick look. So let's have a look here to begin with. Oh, sorry, I went too far there. So this is Buffalo Bayou. All right, so this is going to be the river here. So this is going to be, where am I? Houston. There's Buffalo Bayou here. This is the river coming along the western side of Houston. Okay, and going to the city center of Houston, then heading out eventually into the bay. So we can see in this area, we have a situation where the river's level was normal, and then all of a sudden, whoosh, look at it go up there, really piling up very quickly, plowed through all these very, very fast, and was, into a major flood very, very quickly. And obviously, as we can see, the flood waters took a very, very long time to die down. That's simply the result of the area being so badly flooded, it was going to take a very long time for the water levels to drop. Oh, sorry, so that was the San Jacinto. I was talking over here, sorry, about Buffalo Bayou. Sorry, what am I saying? Same thing though, water goes up, we reach a peak very, very quickly, then the water comes down, in this case, very, very quickly. Now notice for a second where the peak occurred. So notice the peak has occurred just before about 2 p.m. on Monday. Okay, so it occurred sometime around Monday morning. Now, if we look up here at the San Jacinto rivers, what do we see? Well, we do see the discharge comes up very, very fast. Once we reach the peak, the discharge takes a very, very long time to go down because there's lots of flooding in the area. But if we notice when the peak occurred, it occurred very, very early on the Tuesday. So the San Jacinto River was a day behind the west side of Houston. And that's simply because the hurricane was moving northeastward. So it started on the west side of Houston, essentially started flooding on the Monday, and then didn't make it to the eastern side of Houston until the Tuesday. So what we're seeing there is we're seeing the steady migration of the hurricane, across Houston. So the storm was moving from west to east, so it starts over here, so it hits Buffalo Bayou first, and obviously the San Jacinto River is, where are you? There it is, coming down here. Okay, so it took much longer to actually hit that. So there were other considerations as well. One of the other things is that there's Lake Conroe up here. Now, obviously, you have a situation. So if you happen to be part of the municipal team around Lake Conroe, your job is obviously to stop the houses in your area flooding. And so there were lots and lots of local bodies in the area around Houston, that decided that the thing to do would be to let water leave things like reservoirs and lakes in order to try and relieve the pressure in their area. And that would allow the water to flow further downstream. The problem was further downstream of these lakes was Houston. So what we have is a situation where up at Lake Conroe, they had to relieve a little bit of pressure. So they released some water, and of course that's going to come down the west fork of the San Jacinto River here. Okay, so that's obviously going to increase the chances of flooding in this area. So, it makes perfect sense if you're in the Lake Conroe area to do that, but obviously it causes further problems downstream. So in terms of the flooding itself, what can we see? Well, we can see that we have very, very significant amounts of flooding over here around the Addicks Reservoir and the Barker Reservoir, where they've been allowed to flood backwards. Obviously, we have substantial amounts of flooding within the Beltway here, which you would expect, and you can see that all the flooding essentially is picking out the streams very, very clearly. You can see exactly where the rivers were, can't you? Now, if we just come over here for a second, we can see we got Halls Bayou coming down here, and we got the San Jacinto over here. Okay, so we can notice in this area, which is the San Jacinto in the Halls Bayou area, we'll notice that there's quite a lot less damage. And so obviously the question then becomes, why? Why is there a lot less damage over here compared to over here? And the answer is, it's a simple question of urbanization. The density of housing over here is a lot lower than the density of housing over here. Far more houses over here. That means far more urbanization, far less grassland, far fewer trees, and therefore a much more damaging flood. In comparison over here, far, far, far fewer homes. That means more grassland, more trees, and the damage from flooding will be reduced. Okay, so that was our own local flood. So next question is, how do we estimate flood discharge? Well, flood discharge is based on historic data. So when we're talking about a 1 in 100 year flood, what we're typically talking about is the largest flood within a 100 year time frame. Now, one of the things we know is that smaller floods happen quite commonly, and very, very large floods happen rarely. So that means large floods will happen will have quite a low frequency, essentially. So you can see in this graph here, as the size of the event gets higher, the frequency, sorry, as the size, let's try that one again, shall we? As the size of the event is low, the frequency is high. As the size of the event increases, the frequency steadily gets lower. So that's not really a huge shock. Now, this is the kind of data that we get, that we can see. So these are yearly flood totals, or yearly river, or maximum discharge totals for each year. From, in this case, this is Mercer Creek, and in this case we have the Green River. And so you can see, we have all these peaks, and all these are areas where clearly we've had much higher discharge, and these are areas of periods of quite low discharge. So the problem is that the 1 in 100 year flood will vary depending on the data you select. So if we were to select the data in this in this grey area here, well, the 1 in 100 year flood would be here, 1956, and essentially would be right there, wouldn't it? About 72. And in that case, the stream flow in cubic feet per second would have been about 400. So if you're using that as your 1 in 100 year flood, obviously you're going to say, right, as soon as I'm here, that's a major flood. In contrast, if I was to use the data from 1978 to 1994, you can see the major flood is here. Okay, and what about 1987-88? And so in this case, the 1 in 100 year flood would have a stream flow of about, well, in excess of 800 cubic feet per second. So depending on the data, it affects the size of your 1 in 100 year flood, and that will obviously affect your planning. Because if your 1 in 100 year flood is only 400 cubic feet per second, well, maybe a smaller area will be flooded, and maybe that kind of flood will do less damage, so you don't have to plan quite so well. In contrast, if your 1 in 100 year flood is in excess of 800 cubic feet per second flood, well, that means lots of water, lots of damage, and you have to plan well. So depending on what you select as your 1 in 100 year flood is obviously going to affect your planning. The other thing is, you'll notice, is that what we can see there are stark differences between this period for the Mercer Creek and this period for Mercer Creek. And so what we're probably looking at here is we're probably looking at the effects of urbanization. Probably looking at the loss of grassland. So we had plenty of grassland and plenty of trees over here being replaced by cement and asphalt over here. And that leads to water entering the rivers more quickly and therefore higher peak discharges. Now if we look over here at Green River, we can see the 1 in 100 year flood from 1937 to 1961 was up here, and it was somewhere in the region of, I'd say, about approximately 28,000 cubic feet per second, so a pretty substantial flood there. In contrast, the period from 1962 to 1994, we can see the maximum flood would be here, about 1977-ish, and that had a stream flow in cubic feet per second of about, give or take a little bit, about 12,000 cubic feet per second, so considerably lower. And so once again, depending on where you take your data from, it's going to affect your 1 in 100 year flood. So you can skew the data if you want with these particular things. It depends on the data you choose. Now in the case of Green River, you'll see discharges have actually gone down. So that would suggest that maybe they reforested, maybe they cleared some more grassland, maybe they built a dam, something that helps to essentially reduce the discharge or peak discharge of the river during the year. So we also need to think about something which is called the recurrence interval. This essentially says how often will a flood occur. So it's based on the probability that a given event will be equaled or exceeded in any given year. So how do we work out the reoccurrence interval? Well, the reoccurrence interval R is 1 plus n. So n is the number of records. So if you've got 30 pieces of data, n is 30. If you have 20 pieces of data, n is 20. So 1 plus n, and then you divide that number by m. And m is the rank. So the biggest flood will be ranked 1, and if you have 30 pieces of data, the smallest flood will be ranked 30. So what we can see is that the recurrence interval in years gets higher the larger the discharge, which makes sense because we know bigger floods tend to happen far less frequent, whereas small floods tend to happen with a much greater frequency. And so, this gives you some idea about how likely your area is to be affected by a flood. And the recurrence interval is actually quite important. This is one of the things that insurers use to try and work out whether your home is a flood risk. So here we go. So this gives us the same kind of thing. So this is the flood reoccurrence interval in years. Okay. So this is every 1 year, and this is every 100 years. This is the discharge in meters per second. Now that doesn't really matter because that's going to vary per river. But it's this part that's the interesting bit up here. This is the probability of occurrence each year. So as you can see, a 1 in 100 year flood has a 1% chance of occurring each year. So a 1 in 100 year flood doesn't mean that, once every 100 years a flood of that size is going to occur. What it actually means is there is a 1% chance that every year a flood of that size will occur. So the meanings are actually slightly different. If we're talking about a 200 year flood, there is a 0.5% chance a flood of that size will occur each year. A 500 year flood, there is a 0.2% chance a flood of that size will occur each year. So Harvey was said to be a 1,000 year flood. So the chance of that flood was 0.1% per year. So the probability in percent is simply 1 divided by the recurrence interval, which is here. So, and once again, remember, the probability essentially shows you what's the chance of it happening each year. So what an insurance company will do is they'll take the recurrence interval for the area around your house, and they'll calculate a probability based on that, and they'll work out whether your house is safe to insure or not. So if we just come here a second, so we're going to have a look at this graph here. So this is a graph for the Yellowstone River. And if we have a look at the largest flood, well, what's the largest flood recorded for this river? It's going to be up here. We can see about 10,000 cubic meters per second. However, what would the answer be if you were looking at the data just up until 1965? So none of that data actually existed. Well, the answer would be, it would be one of these two events. It would be, just about 7,200 cubic meters per second. So once again, the probability that a flood will occur, you can skew the data. If you select the data you want, you can make the probability higher or lower. So just bear that in mind when we start talking about a 1 in 100 year flood and things like that. The data is extremely pliable. You can make it say what you want if you're being a little bit unscrupulous. So essentially, if we have a look at this graph here, so cubic meters per second, so that's the annual peak discharge. We can see once again the annual peak discharge, the probability essentially decreases as the annual peak discharge increases. So the chance of a large flood occurring gets smaller every year. Okay. So what is the probability that each year that the stream flow will reach 1,000 cubic meters a second? So in that case, we would take a line across until we hit the trend line. We would take our line down, and the chance of that kind of flood occurring is about 15%. So there's a pretty reasonable chance. It's about a 1 in 10% chance that your house will flood every year. So that's a pretty significant chance. So if your river goes over the top of its banks at 1,000 cubic meters per second, so if floods occur above this number, then the insurance company is going to go, there's a 1 in 10 chance your house is going to flood every year. I don't like those odds, and they're not going to insure you. So the final thing is, well, how do we control floods? All right, how do we stop them from happening? Well, the obvious answer is dams. You build a dam, You stop the water from moving down the river valley, you contain it for a while, and you release it in a controlled fashion. Simple. The next option is artificial levees and flood walls. So obviously your river floods when it goes over the banks of the river. So how about you just make the banks really, really high? And so what you can do is you can artificially build levees by simply piling up loads and loads of soil along the banks of the river, making the levees of the river, essentially the banks of the river, really, really high. Or you can build what are called flood walls. And flood walls are concrete panels that you literally just stick into the ground and hold in place with big steel supports. And they form essentially a flood wall, an artificial barrier to stop the river flooding. Then we have wise land use, which is always an obvious one. Reforest land, rebuild wetlands if you can. Okay? Don't build on the 1 in 100 year floodplain. It's a pretty obvious thing not to do. If you can avoid building on it, don't build on it. If you can avoid cutting down the trees, don't cut down the trees. Don't cover the grassland if you can. If there are wetlands in the area, don't drain them, because wetlands are really effective at slowing down the movement of water down a river. The next thing is channel straightening. And channel straightening essentially removes obstacles like meanders. So it means instead of your water wiggling its way down the river and taking ages to get there, you make the river straight. So the water just goes straight from point A to point B as fast as possible. Now that's a method of essentially getting the water out of the river system with the maximum efficiency. It's actually a method that's been used extensively by the Japanese. They've straightened a lot of rivers, especially in the large cities, to get the water out of those large cities as fast as possible. Then we have spillways, artificial rivers and bypasses. So we can see one up here in this diagram. So here's our river. And what it is essentially a spillway or an artificial bypass or artificial river or bypass. Essentially, it's a man-made river. Now, you don't use it all the time, though. What happens is when your river starts to get too close to its flood stage, you open the gates and you allow some of the water to drain out of your river and use, essentially, the bypass, the spillway, the artificial river. Now, the bypass is not designed to stop the flooding, but it's designed to stop the flooding in one area. So the bypass will take water from here and it will transport it down to here. So it will stop flooding in this area right here. It will mean down here there'll still be flooding, but in this area up here, the chance of flooding has been reduced. So a bypass will once again, it'll try and take the water away and release it back into the river at a point where it's going to cause minimum harm. The final option is channel dredging. And that simply is when you use a dredger just to simply scrape the bottom of the river. That increases the depth of the river channel, and therefore that increases the volume of water that your river channel can hold. And that's it. Okay, everyone, good work. I'm sorry part 4 was so long, but well done for sticking with it. By the way, the code word for today, my daughter made today's choice. So today's code word is going to be unicorn. I repeat, unicorn, like the mythical animal. Okay, everyone, thank you for sticking with me. Have a good day, and I'll see you next lecture.